Today we will talk about the 5 normal forms for relational databases, about their meaning and purpose from a practical point of view. To illustrate normalization, I will be using the data of my fictional cat hotel, and I will be using the story of an 11-year-old girl. The whole story is in my other videos, but just for now, long story short, so she's an 11-year-old girl. Her name is Gianna, and she is a beginner developer. She has this idea to create an app to reduce kitchen waste, and she is creating a database. I am helping her to improve the database design by normalizing the database. So let's get into it. So Gianna, let's take this table of yours. What is this table about?
The idea is to collect data, how cats react to various foods. This would be recorded by our hotel staff.
Okay, so basically each row is an observation where the member of staff brings the food and records the outcome. For example, here on the 28th of September, they brought sushi to Bita. She was suspicious at first, and then afterwards half of the food was left over and there was a throw up, right?
Yes.
Let's redesign this table in such a way that it satisfies the first normal form.
I looked up the requirements for the first normal form, but I don't understand them.
So the whole point of all normal forms is to do two things. Number one, to safeguard your data from anomalies, and number two, to make it easier to work with the data. Each normal form has its own way how it approaches these two things. They are numbered from 1 to 5 because they are supposed to be implemented exactly in the sequence. So you don't do the second form before you are done with the first, and so on. Also, the first normal form is the most important and it's a must. And the fifth normal form is already pushing it a bit too far in most cases. So let's focus on the first normal form. And let's name this sheet as first normal form. The way that first normal form safeguards the data from anomalies is by ensuring three things: atomicity of data, consistency of meaning, and uniqueness. So let's take atomicity. It means that each table cell must consist one item, and that item must be in its most basic and indivisible form, just like an atom. Because when the data is not atomic, then you run into all kinds of difficulties and problems. For example, let's take here the amount of leftovers, and imagine that we wanted to sort this table by the amount of leftovers in such a way that 100% was at the top of the table and 0 at the bottom. How would we even do that here? That's just not possible. Or imagine we wanted to collect all instances when a cat threw up. How we would do that here? Now that's possible, but this information is buried inside of the data cells, which means that we would have to read the whole contents of the cell, find this phrase, and only then pick the row, which is inefficient. But on top of that, what if somebody misspelled this phrase? Well, then we would miss the row completely. That makes it inefficient and inaccurate. Then let's take consistency. That means that each column has to have the same meaning and the same data type, and there has to be only one column for each type of information. In our table, that's exactly what happened here. You see the leftovers is recorded as text. So somebody recorded it like this, somebody recorded it like this, and then who knows, maybe someone even records it like this, which is also a valid way, but it's very inconsistent. And as long as this is text, we have no way of enforcing it. And the last point of consistency, that there has to be only one column for one type of information, will become clear when we start fixing the table. For now, we can let it pending, but let's not forget it. And the third point, uniqueness. That means that each row has to be unique, and we have to ensure that if we add a new row that it will also be unique. Our table does not ensure that these rows are different from each other, but it could easily happen that staff on the same day brings the same dish to the same cat and then also happens to have exactly the same outcome. For example, like this. And then looking at this data, how do we even know if this is an accidental duplication, which would be okay, we would just deduplicate data, or did this actually happen? Did someone bring sushi to Beta again after she already threw up and then they did the same thing again? Well, that would be a problem. That's why we need to know. Now we will solve all these 3 points: atomicity, consistency, and uniqueness, one by one. For atomicity, let's identify information that consists of more than one item inside a cell. A date is atomic because this is a single point in time. Next, the cat. And this is not atomic, this is 2 items. So this Beta, for example, is a nickname how a human calls their cat. And this is cat's name the way it is in the passport. That is called a composite value, and it needs to be split into separate columns. So let's do it. Next, the dish. Well, how many items are in a dish?
At least 3, but it depends.
Yes, exactly. This is a little bit more complex than cat. So really, this is 2 types of information. One is the name of the dish, and the other one is the ingredient list. But the ingredient list is a multi-valued information. So it's one type that has multiple values. We tackle that in 2 steps. First, the composite part. Oh, I forgot. Now here we have one type of information, but it's multi-valued. And we cannot solve multi-valued information the same way we solved composite. Let me show you what happens if we try it. So that would look like this. And remember what we left about consistency just a little earlier, that for one type of information there should be only one column. And here we have one type of information, ingredients, but 2 columns. That violates consistency and causes all kinds of problems. One problem is that we have empty spaces, so that's of course a waste. But also imagine that we need to find all occurrences where salmon was served to a cat. Where do we look for that salmon? In one or the other column? I guess we then check both columns, but then imagine that we add a new dish that has 3 ingredients. Okay, then we need to extend the database. We need to add a 3rd column so that we can store the 3rd ingredient. We have even more empty space. And then we also have to remember that we need to update an app, because when we were looking for the salmon, we were checking 2 columns, and now there's 3 columns to check. And if we forget about that, we are going to be missing the thing. So this becomes complicated, and there's plenty of opportunity for mistakes. And the inconsistency of this multi-column situation is that we have one information, ingredient, but it can be either here, or who knows, somewhere else. And we can't be sure. We need to design data in such a way that if there is certain information, then we know where do we find it.
But what's the solution then?
You are not going to like the solution for now, but bear with me. So when we can't split things into 2 separate columns, then the only thing we can do is to split it into separate rows. This is how we do it. So we take the salmon, we put it here. Then we don't need a separate column, but we do need to fill this. So we need to duplicate the information.
But there's more duplications now.
Yes, we have this data redundancy or duplication, which is a waste, but the thing is that the first normal form allows it. We will deal with this duplication when we do the second normal form, but right now we're not violating the first. Right now let's finish with the first, and we have one more column to go. And here we have 3 pieces of information, and each piece consists of name and value, except the last one. So reaction is the name of the information, so that will become the name of the column, like this. And this is the value itself, so it will go into the cell like this. Same here, this is the name of the value, becomes the column name, and the value becomes the content, like that. Now this we can make into a number, and we can enforce constraints. And to make sure that we understand the meaning of this, we can also designate the units here. This is a fact that either happens or not. So that's an ideal candidate for a Boolean value, and I'm going to do it like that. Now everything is atomic and consistent, and each column has its own data type. So this is date, this is text, 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 number, Boolean. All good. Yes, we do have duplication right here, but we'll deal with that when we do the second normal form. We still have one more thing, uniqueness. And we're still not ensuring uniqueness here, because we could still have that situation where I said that the same day, same food, same outcome. In order to solve that, what we can do is turn date into a timestamp, like this. Timestamp is a very common data type, often preferred over just date. And the precision of timestamp in PostgreSQL is to a millisecond. So for us, it would be practically impossible to have 2 events occurring exactly at the same time. Now, in reality, we should just add an ID column and it would solve the uniqueness thing. But I want to leave it here as a timestamp, and specifically this duplicated timestamp, because that allows me to explain the second normal form. But before we go on to the second normal form, do you have any questions so far?
Yes, about this cat, Beta, and Sushi. I saw it on camera recordings, and I'm curious what happened there.
I remember it was a misunderstanding. So Beta's human left a note saying that she liked sushi. What he really meant was sashimi, so without the rice. Which makes sense. Why would you give rice to a cat? But since we're used to all kinds of weird requests, chef just made sushi. And when she threw up, we checked in with her human and we clarified that it had to be sashimi. Next time we served sashimi and everything was fine. To go on to the second normal form, we need to revisit the uniqueness and set the primary key. So the primary key is the column or more than one column that makes the rows unique. Here we created timestamp for uniqueness, but that alone is not enough because one observation will have the same timestamp, and what makes these rows different is the fact that we have different ingredients in this row. So we need these 2 rows for a primary key. Let's mark both of them here. And let's take this. Let's start a new sheet for the second normal form. And let's copy over our data here. Okay. The official requirements for the second normal form are: number 1, the table must be already in the first normal form. And number 2, all non-key attributes must depend on the entire primary key and not just part of it.
And again, I don't understand, especially that second requirement.
That's okay, because we will talk about the purpose of the second normal form and it will become clear. So the purpose of the second normal form is to get rid of data duplications or redundancy and to ensure that if we need to update one piece of information, then there is only one place where we have to update it, and we don't need to worry that we also need to update something else somewhere else in order to avoid anomalies in the data. These two are basically the same thing. The redundancy is a simple way to see the problem, and the why behind why we do it is that so we don't cause anomalies when we update data.
Can you give examples? How we would cause anomalies?
Of course. So let's take this observation that is currently split into two rows. And let's imagine that the staff leaving the room, having already recorded this, actually looks back and thinks, hey, that's actually more like 70% and not 50%. And they decide to correct the data. They start correcting it to 70, but then for whatever reason, something happens, some maybe bug. And the update only affects one of the places, but not the other. And then we would have different numbers when there should really be same numbers. And this is a data anomaly or also a violation of data integrity. And we need to do everything possible to avoid cases like this. Right, so let's look at that requirement once again. All non-key attributes must depend on the entire primary key, not just part of it. This speaks of full dependency versus partial, and here's what it means. So let's say we take this outcome that was recorded, and we know that it is about the whole feeding event. It's not about one ingredient, right? So this data describes this event that occurred at this specific timestamp, which means if we have this timestamp, then we know what reaction it was. Whether it's rice or it's salmon, that does not influence what reaction we have, which means that this data is connected only to this part of the key, but this part does not change anything. See, we have different ingredients, but we still have the same outcome. So this part of the key does not influence the rest of the data. And same with all other data actually. Here, if we know the timestamp, we know the cat. But if we have a different ingredient, that does not change which cat we have here. And when you see a partial dependency, that means that more than one thing is trying to fit in the same table. And in the database design, we're really trying to designate one table for one thing, or in data speak, for one entity. And when two things try to fit into one table, that's when we get duplication, so redundancy, and anomalies. So one of these things has to be separated into another table. And a partial dependency is a way to see where is that other thing that has to be separated. In our case, everything depended on timestamp and not on ingredients. And that is a sign that ingredients is that second thing that has to go out.
But we cannot just take ingredients out. We need to know which dish has which ingredients.
Exactly. When we separate two entities, we still have to preserve the relationship between them. Ingredients belong to dishes, so let's take both of them and put separately. Then we no longer need ingredients here, but we keep the dish because that is going to preserve that relationship. If we know what dish is, then we can go here and from there find all the ingredients. That's the link. And this link is also called foreign key. So this was the primary key. Then this is the foreign key, which allows to connect the data from here with the data that's elsewhere.
Just like people. They can't live together, but they still share the keys because they still need the relationship.
Ah, and one last thing we need to do here is, now we don't need to duplicate this over 2 rows because we don't have the ingredients, which was the whole reason why we duplicated, so we can leave 1 row for 1 observation now. Let's verify once again if this is now in the second normal form. So the criteria was that a non-key attribute should not depend on part of the primary key. Now that our primary key is only 1 column, there's simply no way to violate the second normal form because that's the whole key. You cannot have a part of it. And this table is also in the second normal form because we have no non-key attributes that could violate by depending on part of the key. So all of this is in the second normal form now.
Second normal form was so much quicker than first.
Yes. And I have good news for you. Third normal form is going to be even quicker because it's very similar to the second. It's so similar that actually we're going to stay on the same sheet. We just call it second and third normal form. So the purpose of third normal form is exactly the same as for the second normal form: to get rid of data duplications or redundancies, and to ensure that if we update something, then there's only one place to update and we don't have to worry about updating something else somewhere else. But the way that the third normal form takes care of it is somewhat different from the way that the second normal form does it. So let's compare the two. For the second form, we needed to ensure that the non-key attributes do not depend on a part of the primary key. And for the third one, it should be so that no non-key attribute depends on another non-key attribute. So we're not talking about the primary key anymore. Now, the focus is only on the white parts, and they should not depend on each other. The dependency means that if we change one part, we also need to change the other part. That would be the dependency, and we must not have that. So the example of dependency is this: the name of the cat and the full name of the cat. So this is the same cat. Imagine that staff, after recording this data, realized that this was the wrong cat. It was the same color, same breed, so they mistook it for Beta, but really that was a different cat whose name is Beryl, nickname, Beryl the Peril, full name and the password. So now they need to correct the data, and they need to correct both of these. And they correct the nickname, but then again, for whatever reason, the second part of the correction fails, and we end up having changed only the nickname, but not the full name. And now we have this situation where this cat does not exist, anomaly, and a violation of data integrity.
Is the solution the same then? Separation?
Yes, we need to identify the entity that causes this and then to separate it out. And of course, here this identity is the cat. So let's take the cat out, and we are going to do this a little bit differently. In this table, we still need to take care of uniqueness, because we could, if we have a Moggy cat whose name is Lucky or Princess or Amax or whatever. So we have to add ID here, which in the database we are going to make it so that it auto increments. And then here we replace this with ID like this. In reality, these IDs are very convenient, and in the real database we will eventually have IDs in all columns, but just here for now we're only going to have them where they're only absolutely necessary. This is the foreign key. Yes, so cat ID, just like dish name, is going to be a foreign key that preserves the relationship between this table and this table. And now we have a design that satisfies all 3 normal forms. We did a good job.
Aren't there 2 more normal forms?
There are a 4th and 5th. Here I have more good news.
They are even easier to learn?
Better than that, and they are not even necessary. So in most cases the first three forms are enough, and especially if you're just starting out and that's your first iteration, then you don't have to worry beyond the third normal form. Only when your database is getting more complex and you have specific types of data, then you might have a look at fourth and fifth.
But since we learned the first three, why don't we go all the way and learn the remaining two?
Actually, those two remaining normal forms are a bit trickier, but we are going to unpack them. Let's start a new sheet for that. Okay, let's copy our current situation here so that we can see it. But the thing is that this data is not complex enough for us to demonstrate the fourth normal form. Like I mentioned, in most cases the first three forms are enough, and that was exactly our situation. But I can imagine how you will need that fourth normal form, so let me add some new data here. When it comes to feeding cats, we are going to need to know their preferences and allergies, right? Let's create that. And let's say that the first one, who is a beta, prefers salmon, of course. And let's say she has an allergy to rice. But also, let's say that she also likes squid. And chicken liver obviously likes chicken liver. And say she has two allergies to dairy and eggs. You can already suspect what's the problem with this table, right? So first of all, we have these empty spaces, which is a waste. But the bigger problems will happen when we try to update the data in the table. Remember what was the purpose of the second and third normal form? To get rid of data redundancies and to make sure that if we need to update something, then there's only one place to do that and we don't worry about anything else. Same here, exactly the same thing. The fourth normal form wants to ensure that no redundancies and the update happens only in one place. What happens here if we need to update something? Let's imagine that beta no longer likes salmon. What do? We can't delete the whole row because we would also delete her allergy. So then we delete just this value. But then we end up with this funny situation where we have these two empty cells, and really the whole data should fit into one row. Why would it be split over two rows? Shouldn't we then do some kind of cleanup and collapse them into one? Or imagine that chicken liver starts liking goose liver. Okay, simple way would be to add it as a new row, goose liver. But then again, we have this empty situation here. Shouldn't we actually add goose liver into the empty cell like this? It would be better to save space. But then what if she has more allergies and then we have more than one empty space? Now we need to choose where do we record it. So you see that something that should be a very simple operation to add or to delete turns into some kind of a multi-optional decision-making exercise. And that shouldn't be so complex because that opens the possibilities for all kinds of anomalies. Now that we understand the problem, let's look at the requirement for the fourth normal form, which is, of course, everything has to be in the third normal form already, and there should be no multiple independent one-to-many relationships. By the way, I admit that I already translated this requirement into something that's more like a human language so we can understand it, and the official requirement does not sound so understandable. But let's unpack it now. So, no multiple independent one-to-many relationships. What is a one-to-many relationship? Well, that is where we have one cat but many preferences, and one cat but many allergies. And importantly, they are independent of each other, which means that if we know that a cat prefers salmon, that doesn't automatically tell us that she also is allergic to rice. Yeah, these two are not related. And also, rice could be here, it could also be here. There's no difference. So that tells that these are independent of these. And this is exactly what causes this problem with updates and anomalies.
So, just like people, if they are independent, they don't want to share the same space.
Not quite. If they are independent and they have a lot, then they can't live in the same space. Note that earlier, all of that data was actually independent. Say, if we knew what cat was it, that didn't mean we knew automatically what would be the reaction. So there were already independent data items, but the thing is that they did fit into one table because each of them had only one value. But here we have multiple values, so there can be many preferences and many allergies. So the two independent entities, are fine with being in one space as long as all they have is one thing, one value. But as soon as they start having more, now they don't fit.
So, the same situation, separation again?
Yes. Although in this case, I guess we could also solve it by limiting to having only one value. So, for example, if we decided that a cat is only ever allowed to have one preference and one allergy, then we wouldn't have to separate. But of course, we're not going to do that here. So we will have to separate. And that's rather simple. So one-to-many relationship goes into one table, and the other ends up in the other table like this. And that's that. That's the fourth normal form. Now, if we want to delete a preference, we simply delete one row. If we want to add a preference, we just add one row. Simple.
It is indeed simple.
Okay, now the trickiest of them all, the fifth normal form. Let's stay here on the same sheet, but we will need new data because once again we need additional complexity for this. If for the fourth normal form we needed two independent one-to-many relationships, then for the fifth normal form we need three-way dependent relationship. Let's create some data that has that. Let's say we have dishes and ingredient, and ingredients come from suppliers. And for sushi we need rice, and let's say that it comes from two different stores. We also need salmon, which also comes from both of these. For sashimi, we only use salmon from Waitrose, and for chicken liver, obviously we need chicken liver from a local farm or from the shop. Now, importantly, this is a three-way relationship, which means that there is a relationship between the dish and the name, pretty direct relationship between an ingredient and the supplier, and also we need the relationship between the dish and the supplier for it to be a three-way relationship. So specifically, look at what I did here. If we have sushi, then we can get salmon either from Tesco or Waitrose. But let's say that our chef made this decision that sashimi is a dish in the more expensive category on our menu, so we only get all ingredients for sashimi from the more expensive store, which is the Waitrose. So there is also a relationship such that for certain dishes, we get ingredients from certain suppliers. Yeah, we need that for the three-way relationship. And we can't solve it by splitting this into two tables, because in two tables we would only be able to capture two relationships. And here we have three. So we need three tables, right? And let's do that. But before that, let's talk why we need it at all. Yeah, because we don't split things without a good reason. We need the reason. One last time, let's remember the purpose of the normalization, which is still the same like second, third, and fourth. get rid of data duplications and to ensure that if we update something, we only do that in one place and we don't have to worry about other things. So that's the same thing here now. Obviously, we have plenty of duplications and redundancy. And let's see now what happens if we want to update something. So let's say we have a new dish. Let's say we have liver biryani, which we made from liver and rice. Chicken liver, which can come from these two, and rice, which can come from these two. So now look what happened. We created a new dish with 2 ingredients and we had to add 4 rows. Or even worse, imagine that we have a new store opening nearby, so now we can get all ingredients, rice, salmon, chicken liver, and from that store, let's say it's Sainsbury's. How much data we would have to add just because we have a new store? Because we would have to add it for every ingredient and for every dish. Yeah, so we would have to cover all of those combinations. Plenty of opportunity to miss something and to get a data anomaly, right? Typically, it is easier to manage 3 small tables than 1 big table. So let's try to split this into 3 tables. We have 3 relationships here, and we're going to designate 1 table for 1 relationship. So one of them is between the dish name and ingredient. The other is between ingredient and supplier. And the third one was between the dish and the supplier. For sushi, we were using Tesco and Waitrose. For sashimi, we were using only Waitrose. So this is how we capture that information here. So now this is in the 5th normal form.
And where's the new dish, liver biryani?
Yeah, so if we needed to add this new dish, this is how we would do it. Dish name and ingredient is added like this. Ingredients are already covered here. Dish and supplier. So we have this dish and we have 3 different suppliers. Like this.
So we had to add 5 rows. That's more than before.
Yeah, that's a good point. I guess you could say that 3-way relationships never get really simple, no matter what you do. It's still simpler to manage 3 smaller tables than 1 big table when it comes to handling all the transactions and data integrity. But you can see how this benefit becomes debatable because we still have a lot to do. And the other thing is that not always it is a good idea to separate into 3 tables because we may be losing information. And I will give you an example of how we can lose it. So remember here, when chef decided that for sashimi we get ingredients only from Waitrose because that's a more expensive dish. Okay, so the change was in this relationship between the dish and the supplier. But imagine that when we have a biryani dish, then we only get rice from Waitrose and not from Tesco because only Waitrose has the right type of rice for this dish. If we have this original table, then we delete this row. But if we have these 3 tables, then we can't capture this fact that we don't use rice for liver biryani from Tesco. Because how we would do that here, look, we can't delete biryani here from rice because we still need rice, only it has to come from a different supplier. And we can't delete this one, biryani and Tesco relationship, because we still use Tesco to buy chicken liver for the liver biryani dish. And so we can't get rid of that. So there's no way that we can capture this fact when we have everything separated. And this happens because this is information that is encoded in the 3-way relationships, not in separate 3 2-way relationships, but it is encoded in 1 3-way relationship. You need all 3 to come together to create that data. Yeah. And when you have that situation, then the only way you can record it is to keep all three in the same table, right? If you have three two-way relationships, then you lose the possibility to have that data, that three-way data.
This one was tricky, but I get it.
Good. Can you recap the most important points now?
Sure, all normal forms exist to protect us from data anomalies and to make it easier to work with data. The first normal form is the only one concerned with atomicity, consistency, and uniqueness. The remaining normal forms are concerned with duplications or redundancy and ensuring that updating data is done in one place only without worrying about additional updates somewhere else. We implement them sequentially, starting with the first, then second, then third. Most of the time this is enough, but sometimes we do the fourth, and in rare cases, maybe also the fifth, very carefully.
Okay, very good. We have done a lot. I have to say that I thought that this topic was going to be easy. There's already so much information out there, so many videos, but it was such a rabbit hole, and actually there was a lack of good and understandable and consistent explanations. So I hope that my way was at least one of the best ones out there, and that it really helps you. Thank you for your time, and I'll see you in the next one.